Hello and welcome. This is Unit 3, Lesson 2, U-mix cubes. So what we're going to do in this lesson is we're going to connect what you know about parabolas, x squared, with the cubic function, x to the third. So one thing here in the jump start is identifying the key features of y equals x squared. That would, of course, be domain, range, maybe some intercepts. Does it have any asymptotes, things like that. So here's the basics. The domain of the y or g of x equals x squared function is everything. There's no number that you can't square. The range is, on the normal, we would call this the parent function, x squared. So in other words, there's no transformations. That would go from 0 with a hard bracket, so we're going to include 0, to positive infinity. And areas of increase and decrease, or intervals of increase and decrease, well, remember the shape is that it comes down, swoops down, comes back up. So it's decreasing from all the way to the left, negative infinity, until you get to 0. 0 itself is a transition point, so we wouldn't put a bracket on that. And increasing from 0 to positive infinity, the right side. So in other words, comes down and then goes back up. And then one last thing we want to write down is the intercept. And let's learn how to spell it. Intercept. And that would be, the x and y is both at 0, 0. By the way, 0, 0 is also what we would call the reference point. And that means that when we look at shift, this is the point that we want to track. It's kind of like the belly button of the graph. If you know where the belly button is, you know where the person is. Okay, so these questions here would be from last year. Okay, graph each of the following functions using transformations of x squared, right? G of x is x squared. So the first one, this plus 3, that's a shift up. So normally we would go through, here's our x and y axis, and normally we would be going through 0, 0, but that reference point is moved up 3 to here, and then we form that parabola shape. Real quick way to make a parabola shape is to go up 1 and over 1, and then go up 3 and over 1 on both sides of the reference point. So there's what that would look like. B is a shift. You would think it would be to the right, but it's actually to the left. So again, we make our x and y axes. And normally we would be going through 0, 0, but this time we're going to go 1, 2, 3 points to the left and recreate the graph right there. There we go. And this last one, a couple of things are happening to it. So this negative out in front is going to flip it around. It's going to make it kind of a sad face parabola, right? Or crying. But the x minus 1 is going to shift it 1 to the right, and the plus 2 at the end is going to shift it up 2. So you do all those things at once. From the reference point 0, 0, you're going to go right 1, you're going to go up 2, there's our reference point, and we're going to make it go downward. So down and over, and then down 3 and over. 1, 2, 3 and over. And so it looks like this. tricky to do. And there we go. Something like that. So again, we're going to compare this to the cubic function. We're going to graph the cubic functions. The similarities are going to be true for lots of things, not just x squared and x cubed, but maybe x to the fourth, x to the fifth. And then the differences, well, you know, quadratic, does have x to the second power. That's an even number. Cubic is x to the third power. That's an odd number. We're going to find that the even numbers kind of all look the same, and the odd numbers kind of all look the same. All right, so the cubic, as it says here, is a degree 3 polynomial because it has an exponent that the highest power is 3. The degree is the highest power. Okay, so we're going to use a table and verify the quadratic rate of change. That's what we did, well, not yesterday, but the previous lesson, whenever you did the previous lesson. So let's make a table. X, Y, 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. Do we need to do one more? 4 cubed is 64. Okay, then we look at the change between those numbers. So 0 to 1, that's 1. There's 7. That would be, what, 19? And then 64 minus 27 is 37. Okay, we did it once. Now we do it again. 1 to 7 is 6. 7 to 19 is 12. And 37 to 19, or 19 to 37 is 18. We did it twice. We do it 3 times. We have a constant. Okay, so there's our proof that it's cubic as a quadratic rate of change. So these numbers here are quadratic. How do I know? Because if I look at the differences, the second level difference is constant. Or I could just say the third level distance from the original, or difference from the original, is constant. Okay, let's graph that. So again, we're going to draw in our x and y axis. Okay, so it starts at 0, 0. That's our reference point. 1 cubed is 1. 2 cubed is 8. Let's see if we can get there. 1, 2, 3, 4, 5, 6, 7. Oops, missed. So we'll just put one up here. On the other side, on the negative side, if you take a negative 1 and you cube it, you get a negative 1. If you take a negative 2 and you cube it, you get a negative 8. And that's because you have an odd number of negatives. So it's going to go here, and it's going to go, let's see, 1, 2, 3, 4, 5, 6, 7. Man, again, we're off the graph. So if we connect these together, looks something like this. Now, this point in the middle is also called a point of inflection. So let me explain what that means. Point of inflection is where you have a change in concavity. Okay, perfectly clear? No. What's concavity? Okay, so think of concavity as a cave. Or I think of it as a cup. Now, if a cup is facing upward, so it can contain water, and here's our water, or whatever, we would say that's concave up. But if we turn it upside down, and all the water comes splashing out, we would say that that cup is concave down. Well, there's a change in concavity of the graph at 0, 0. See, to the left, it's almost like it's spilling water. And to the right, it can collect water. Now, it's not a perfect analogy because, of course, the water is going to spill over if it was really water. But it has to do with the rates of change. Think of it this way. If you cup your hand and you go like this, here's your fingers, okay? And then you cup your hand, other hand, and there's your fingers. Where your fingertips meet together, that's the point of concavity. That's the point of inflection. Number 3, describe the features of x cubed, including the intercepts and the domain and range. Where does it increase? All that good stuff. Okay, so let's do the domain and range first. Domain. It's everything. There's no number that you can't cube. How about range? Well, that too is everything. You can get to any y value if you're patient enough. The intercepts, the y-intercepts, both intercepts are at 0, 0, so that would be a good reference point, right? And it's always increasing. So in other words, as you pick bigger and bigger x numbers, you're going to have higher and higher y numbers. So increasing on the entire real number interval from negative infinity to positive infinity. It never decreases in its natural state or its parent graph state. Let's go to the next one, number 4. Using your knowledge of transformations, graph without technology. Okay, so here's my x-axis, my y-axis. Let's do a couple of these at a time. Okay, x cubed minus 3. So normally we'd have 0, 0, our reference point. We're going to go down 3. 1, 2, 3. And then we're going to go up 1 over 1, up 8. 1, 2, let's see, 1, 2, 3, 4, 5, 6, 7, 8. And over 1, and then when we go down and left, we're not going to get that last point, but it's going to look something like this. Okay, on part B, we're going to go left 3. 1, 2, 3. We're going to go up and right, down and left. I don't know if we're going to make it here on 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we're not. But it goes up there and it goes down over here. So it goes up pretty fast and it goes down pretty fast. Okay, part C, what happens when you stick a 2 out front? Well, that 2 sometimes is referred to as the stretch. Everything gets pulled twice as far away from the reference point as it normally would have been. So we're still going to have 0, 0. But instead of 1, 1, we're going to have 2, 1, 2 up here and down here. And if we could draw that next point, if we were to go over 2, that would be up 16. So this thing is really, really steep when you put a 2 in there. All right, D has 3 transformations. It has a negative, it has an x minus 1, it has a plus 2. So notice how similar this was to the jump start. It goes right 1, up 2, but then it's got a negative. So what's the negative do? It flips it upside down. So if you can imagine, if you've ever played basketball, the normal cubic is a right-handed layup. So here's your leg, here's your torso, and here's your arm going up. Well, when you flip that or reverse it, it looks like a left-handed layup. Here's your left arm, here's your torso, here's your right leg. So this thing is going to go still up but left, still down but right, and then we'd go to 8. If we could draw it, I think we can get 8 on this other one. So over 1, down 1, 2, 3, 4, 5, 6, 7, 8. Yeah, right down here. So it's going to look like this. Coming through. So kind of backwards. You could say it's reflected across the axis of where the reference point is. Number 5, use technology to check your graphs above. You're welcome to do that with Desmos. What transformations did you get? What areas do you need to improve? Those are all personal kind of questions. So we're going to let you do that. 6, since quadratic and cubic functions are both in the polynomial family, we would expect them to share some common characteristics. What will be those common characteristics? Okay, so they got the same domain. Which is everything, right? Negative infinity to positive infinity. Same reference point or intercept. Oops, got kind of carried away on that. It's still 0, 0. They're both continuous, no breaks. They both increase on 0 to infinity. And the transformations work the same. Again, that works for all the polynomials. The whole family of polynomials would work that way. Number 7, as you can see from the graph of the cubic, there are also some real differences. Each of the following statements describes one of those differences. Explain why each statement is true by completing the sentence. So the range of f of x equals x cubed is negative infinity to a positive infinity, but the range of g of x equals x squared is 0 to infinity because, well, a square number is always positive. A cubed negative is going to go negative. It has to do with the exponent, basically. So even exponents make positive numbers. Let's see, for part B, excuse me, for x is greater than 1, f of x is greater than g of x. So in other words, the cubic is bigger than the quadratic because, again, x is greater than 1. Cubing x greater than 1 makes a bigger number. Than squaring. And between 0 and 1, g of x is greater than f of x. So in other words, the square is bigger than the cube because when you square a fraction, the values get smaller. But when you cube a fraction, the values get even smaller. And you could just test that out on, say, 1/2. Even smaller. Okay, so let's see. Let's do some takeaways here. Similarities, same domain. Um, 0, 0 is going to be the same, the reference point. Continuous. Increase on the same interval. And they transform the same. Differences. Their range is different. The square goes from 0 to infinity. The cubic is everything. Also, f of x, if x is greater than 1, f of x is bigger than g of x. So generally, cubing numbers makes it bigger than squaring numbers. But if you go between 0 and 1, well, that switches around the other way. And last thing is, you notice there's different symmetry in the graphs? So in other words, you can fold a parabola. There's an example here. You can fold a parabola side to side. It has an axis of symmetry. For a cubic, there is some symmetry, but it's reflected through the origin to the other side. We call that rotational symmetry. It has 180-degree rotational symmetry. So what should we write here about just different symmetries? Alrighty, look at your vocab. You got cubic, polynomial, and degree. Remember, degree is the highest power that you're going to see. That's where the cubic gets its name, from a cube, volume, and a square gets its name from a square, the area of a square. All right, well, that's it. We'll see you next time. Have a good day.